Hello everyone, this is Professor DePaulo welcoming you back to Psych 220 Behavioral Statistics, and today I'm going to be talking about sampling distributions. So previously we talked about z-scores and probability, right? And our z-scores were based off of single cases. So we basically transformed a single case into a z-score based on where it fell in the distribution, the normal distribution. So we had z is x minus m over s, right? So x is a single case. We compare that to the mean of the sample, divide by the standard deviation, and it tells us what position is our single case relative to everybody else in terms of standard deviation units. Is it above the mean? Is it below the mean? And how many standard deviation units is it above or below the mean? Now we're going to extend this to samples. So we're gonna extend this z score from a single case. This is a single case to a sample, right? So now we're comparing it to a mean. So z is equal to the mean of the sample minus the population mean over sigma, the population standard deviation, but we have to transform this to something called the standard error of the mean. This is the standard error of the mean. And what does that mean? So this is a sample mean. So we're no longer comparing a single case. We're comparing an entire sample to see where is the sample relative to all other samples that make up the population, right? And this population generally represents the null hypothesis. And we talked about null and alternative in class. So this mean here represents what would happen if the null hypothesis is true, what we'd expect the mean of that population to be. The m is the sample mean that we took. The n is the sample size. And sigma here is the population standard deviation. So in order to use z, we must know sigma, the population standard deviation, right? This is the population standard deviation. We have to know that. If we don't know sigma, then we cannot use z. Okay, so we went from a single case x minus m, or if you want to talk about the population, it could have been x minus mu over sigma, right? These are the same. This is a sample. This is a population. We went from the single case example, right, to what if we have a mean? Can we compare a mean to a population? This population represents the null hypothesis, right? So this is the mean of what would happen if the null hypothesis is true. So is our sample different from what we would expect if the null hypothesis is true, right? And that difference between the mean and the population over sigma divided by square root of n, we call this the standard error of the mean. So what exactly is the standard error of the mean? I want to demonstrate it with a little bit of a talk about sampling distribution. So let's talk about a sampling distribution before we get back to z. So when we're talking about sampling distribution, let's start with the sampling distribution of the mean. So what does this mean? This basically means that if we took a sample of a given size, so I repeatedly take samples of size n, whatever that is, right? Right, whatever your sample size is, it's n, right? And plot the mean. So I take samples of a given size, whatever your n is, whatever your sample size is, and you take it with replacement, and you keep plotting the means of those samples over and over again. And when you do that, something interesting happens. This is what's called the sampling distribution of the mean. Let's take an example. Let's say hypothetically our population is 1, 2, 3, 4, 5. Now, obviously, our population would never be this, but for an example, let's just say that this is the population. These are all the scores of the population. What is the shape of this population? Well, the shape of this population is rectangular. Right, because if you were to plot it, it would look like this. This is just a hypothetical. Here's frequency, right? Here's my x value. So I have 1, 1, 1, 2, 1, 3, 1, 4. So that's not normal. This is uniform, right? Or rectangular. It's not even close to normal. Now let's say I take unlimited samples. Take unlimited, or as many as I can, of size 2 from this population. Of size 2 from the population. From this population. So I'm going to take I'm going to take unlimited samples, as many samples as I can take with replacement from this population of 5 scores. Okay, and I'm going to plot it. So let's plot these samples. Now I know there's 5 scores, right? And if I can take 2 with replacement, sample size of 2 with the replacement, the number of samples or number of possibilities is going to be 2. Actually, I'm sorry. It's going to be 5 to the second power. Let me just erase that. 5 to the second power. 5 possibilities. 2 is the number of items in our sample, right? So 5 times 2 is 25. So there's 25 total possibilities. Let's plot them. And I'm starting with a small problem like this because, you know, theoretically, we're doing this with samples of all kinds of sizes. But once you start getting big samples, plotting every possible sample is impossible. You need a computer to do the simulation, to actually do the simulation of that. So let's plot all from this population. So first one is, well, actually, it's similar to the heads tails tree that we did before, right? Except here I have 1, 2, 3, 4, 5. This is similar to the probability tree that I've done previously. So on the first sample, you can get the first data point out of the sample of 2, right? You get any of these scores with replacement. And on the second one, you can also get any of these scores since we're replacing. So this is how I branch it out. So if I get 1 first, on the first draw, I can get 1, 2, 3, 4, 5, any of those 5 on the second. And the same here, right? And this is going to launch all, or write out all the possible samples of size 2. Because I'm replacing, so it doesn't matter what I get the first time, I can get everything the second time. So you can see there's 25 different possibilities, and these are the mapping out all the possibilities here, right? So all I have to do is map this out. First sample is 1 and 1. Then I have 1 and 2, 1 and 3, 1 and 4. So all I'm doing is copying from the tree. 2 and 1. And I'm making the entire sample space like I did last time with the heads and tails, where I did the multiple trials. I'm putting every possibility, which is creating the entire sample space. And then we're going to look at what happens when I look at sample means. So I'm taking as many or unlimited samples of size 2, as many as I can get, from a population of 5, which is 25 different samples. And I'm listing them all the possibilities here. And there's 25 of them, right? There's a lot of different. Now, this can get out of hand. That's why I kept it small, because you can see that it can get really big really quickly, and then you can't even write them down. There's so many, right? So here I have 25 on a sort of a fictitious problem, a very small set. But in the real world, you're talking about thousands and thousands and thousands of samples. Okay, these are my 25 samples. Let's find the mean of these samples. So I'm going to find the mean of these samples. So I just add them together and divide by 2. And I find the mean. And then I'm going to plot the means. So far I'm just finding means of these samples of 2, right? Still plotting the means. Of all possible samples. So those are my 25 means. Now we're going to plot them. We're going to make a histogram. And we're going to look to see, this is literally the sampling distribution of the mean for size 2 for this population. This is the sampling distribution of the mean, the entire sampling distribution of the mean. So this is basically every sample mean plotted possible. And generally, this would reflect the situation if the null hypothesis is true. We're always comparing our sample in research to what would happen if the null is true. If the null is true, you should get something similar to this situation, the sampling distribution of the mean, right? So you're going to get different means depending on the sample you take, but they're all going to be around a certain number. And when we plot them, we're going to see that. So what are our values? 1, 1.5, 2, all the way to 5, right? So we have 1. Obviously, I'm not an artist on here. 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5. I think that's all the values here, right? And now we're going to plot frequency. Let's do 1, 2, 3, 4, I think 5. I don't think we have anything more than 5 here. Okay, so how many 1s do we have? We have 1, 1. So draw the bar at 1. How many 1.5s? We have 1. We have 2 1.5s. How many 2s do we have? 1. 3 2s. How many 2.5s? This is the sampling distribution of the mean for a sample of 2 scores. I have 4 2.5s. How many 3s? 5 3s. Then we do 3.5s. 4 3.5. How many 4s? 3 4s. How many 4.5s? 2 4.5s. It looks like only 1 5, right? And so we get this. This is the sampling distribution of the mean. So this is every possible sample mean of size 2 plotted. Why is this important? Well, look at it. It's a normal distribution. The population was rectangular. The sampling distribution of the mean is normal. There's significance to that. Remember, we need a normal distribution to do a lot of our parametric tests, our hypothesis testing. Right? And this thing gets us a normal distribution pretty easily, even when the population is not normally distributed. This is a lot different than single scores. When we had single scores, then yeah, whether the population was normally distributed was important, because if the population was not normally distributed, then we had a problem. We couldn't use Z. Here, even with a population that is rectangular, we get a sampling distribution that is normally distributed. Why is that important? Because this represents the null hypothesis pretty much in every hypothesis test we conduct. We're going to look at our sample and we're going to compare it to this sampling distribution of the mean. And if our sample is far enough away or far enough in the tails of this sampling distribution of the mean, then we're going to reject the null hypothesis. Okay, so it's important that this is normal. Now, the mean of this distribution here, right, is 3. So the mean of this sampling distribution of the mean, so mean of the sampling distribution of the mean, that's a pretty tricky thing to say. The mean of the sampling distribution of the mean is equal to the population mean. So if you looked at that population mean, the population 1, 2, 3, 4, 5, and you found the mean, it's equal to this, right? And one other thing, the standard deviation of the sampling distribution of the mean is equal to sigma divided by square root of n. This thing is called the standard error of the mean, or just standard error. So as you can see here, the standard error is always going to be smaller than sigma, the standard deviation of the population, because sigma over radical n is going to be smaller than just sigma, unless n is 1, in which case you don't have a sample. You have one individual score, right? So because we're looking at the variance here, right? The variability in the sampling distribution of the mean is always going to be less than the variability in the population. Because we're looking at differences between means, and those means are more clustered together than individual scores. So the mean of the sampling distribution of the mean is going to be equal to the population mean. And the standard deviation of this sampling distribution of the mean is going to be equal to sigma, the population standard deviation, divided by square root of n, the sample size. This is called the standard error of the mean. And as you can see here, as n gets bigger, what happens to the standard error? It gets smaller. And when the standard error gets smaller, what happens to z? It gets bigger, right? So that's important. That's why a large sample can drive you towards significance, statistical significance. It's because of this, the square root of n here in the standard error. Now, these 2 points that I made here fall under an idea known as the central limit theorem. And let me write that out better. So these 2 ideas fall under the central limit theorem, or the CLT, sometimes we call it. So this is part of the CLT, and this is part of the CLT. The other part of the CLT would be if n is greater than or equal to 30, the sampling distribution of the mean is normal or normally distributed, right? So if our sample size is 30 or more, we are guaranteeing that the sampling distribution is normal. Now, it's normal here, even with a small sample of 2, right? It's normal here with 2, but it's guaranteed to be normal with 30 or more. Now, reasons why this wouldn't be normal with less than 30 is because maybe there's extreme skewness. And so we have to be careful. If we're dealing with small samples, we're not guaranteed normality unless the population is normally distributed. So there's a big or here. Or the population is normally distributed, that will also guarantee the sampling distribution of the mean to be normally distributed. So n is greater than or equal to 30 guarantees a normal distribution for the sampling distribution of the mean, or the population is normally distributed, that will also guarantee a normal distribution for the sampling distribution of the mean. So this all makes up the central limit theorem, which is a very important theorem in statistics. So that's kind of the theoretical aspect. Let's go back to the z-score again. Remember, this is the the single score. So here's single score again. This is population. It could also be sample, right? This is single score. So we're comparing a single score to a population mean, right? This is the single score X, right? This is the single score. We're comparing it to the population mean, which is mu, and dividing it by the standard deviation. We need to know the standard deviation. We also need to be told that the scores are normally distributed because that's not guaranteed, right? We don't have 30 or more. We only have a single score. So we have to be told that the scores are normally distributed to use Z. Now we're moving back to the sample, as I pointed out at the start, right? So now we're not working with individual scores. Why? Because we always work with samples. We always do some kind of intervention, some kind of treatment on the sample, and we compare the sample to see if the sample is different than what we'd expect if the null hypothesis is true. We're not working with single scores. Those are case studies. And case studies might be good in clinical psych, but they're not good in research in general. Because one person does not represent pretty much anything. Right? Definitely doesn't represent a population. So we're not using one person or a single score. We're using a sample. So we're using a sample mean here. But since we're using a sample, we need to use the standard error. So with the single score, we're comparing Z to that table, right? But that represents single value. So we're always dividing by the standard deviation of the population. With the sample, we're looking at a mean, comparing that to the population mean that represents the null hypothesis, right? This represents the null. So we're saying is our sample mean different from what we'd expect if the null is true? But since we're using a sample mean, we have to adjust our measure of variance because the sampling distribution of the mean, right, is going to be less variable than the single score population standard deviation, right? So we have to adjust by using the standard error, sigma over square root of n. And then we're going to compute z, and we're going to determine, what is the probability that the sample either belongs with the null hypothesis population here, or it doesn't. It's going to be similar to using the z table that we did with the single score, but we're just using a sample now. So let's look at that. Now let's look at the standard error again, right down here. This is the standard error. And the most important thing is I can make this small, the denominator small, by increasing my sample size. N is our sample size, right? So if I increase n, I make the denominator small. If I make the denominator small, then the numerator over a smaller denominator will give me a bigger z. And if I get a bigger z, I can then reject the null hypothesis easier. So the goal here is drive up the sample, or sigma, reduce the variability in the population, which is kind of out of your control because it's the population. Or make sure the sample mean is way different than the population mean that represents the null. The easiest one to control here is n, just to increase sample size. If you increase sample size, you reduce the denominator and you make z larger, and you give yourself a better chance of rejecting the null hypothesis. So let's take a look at how that works. So let's say we took a sample of 16 people. We found the mean to be 20. And we're comparing the sample to a population with a mean of 15 and a standard deviation of 6. And I'm asking myself, is this sample, right? Is this sample reasonably different from this population? Or what percent, let me write that a little better. What percent of all scores would be greater than a sample mean of 20? So based on this population here with a mean of 15 and a standard deviation of 6, what percent of all scores would be greater than a sample mean of 20? So we got this sample mean of 20 with 16 people, and we have to find out what percent of all scores. This is very similar to the single sample z test that we did, right? So we did the single score z test before, but now we have a sample mean, so we're going to use this alternate z test. This is called a one sample z test, basically. So z is going to be our mean, which is 20, minus the population, which is 15, population mean, over sigma, which is 6, divided by n is 16, square root is 16. That gives me 5 over 6 over 4. All right. So that gives me 5 over 1.5. And we do 5 over 1.5, we're going to get 3 and change. So what I do is I go into my R calculator to figure that out. It looks like we have 5 over 1.5. So let's look at that. Obviously, you have your calculator. I have my calculator. I just like to do it in R because it's just easier. So 5 over 1.5. And it's 3.333 repeated. That's my z-score. And we want to find percentage of scores greater than this. That's if the table even has it. I don't even know if the table will have that. It's going to be way out in the tail. Here's 0. Way out in the tail here is 3.33. So we want this little tiny, tiny, tiny shaded area. So let's look to see if it's in the table. So I need to go to my table, which is back here under study guides. I'll go down to the table here, and let's look in the table for the 3.33 if it's in the table. And it may not be. Oh, it is. Well, actually, it stops at 3.3. So let's use 3.30 because 3.33 is between 3.3 and 3.4. So let's use 3.3. And we want the tail. And we're really, really out here. 0.0005 is the tail. So this is 0.0005. Move the decimal point 2 spaces to get the percent. So it's going to be 0.05%. So 0.05% of all cases, of all means, of all samples, right, would have a mean greater than 20. That's not a lot, right? So what that's telling me is that if you have a sample with a mean of 20 from this distribution with a mean of 15, right? Because the mean here is 15. If you have a sample with a mean of 20, it probably does not belong to the distribution with a mean of 15. So if this represents the null hypothesis, and my sample mean is 20, I'm getting this large z-score, it's very unlikely that this is a random sample from this population representing the null hypothesis, right? This is mean here is 15, right? So when I'm out here at 20, it probably doesn't belong with this distribution, right? It belongs to some alternative distribution. And so I would reject the null if I'm testing a hypothesis because this percentage is so small. It doesn't belong with the null. It belongs to some alternative that's greater than 15. And we're going to talk more about that next time. But this is just an example of how to conduct the z and look it up in the table. So let's look at another one. Let's say that I'm dealing with a sample where my mean is 25. My sample of 25 students, I should say, where my mean here is 70. And I'm comparing that sample to a population with the mean of 75 and a standard deviation of 15. So I'm comparing this sample to this population, and I'm saying, is this sample different than this population? Basically, another way of saying this is, could I get a sample with a mean of 70 typically from a population with a mean of 75 and a standard deviation of 15? How likely is it to get a sample of 70, sample size 25, right? So let's do that. Once again, z is mean of the sample minus the mean of the population over sigma divided by square root of n. Here we have 70. Here we have 75. 15 over square root of 25. Here I have 5. Here I have 15 over 5. This gives me 5. This gives me 3. We get 1.67. So that's my z-score, and I want to see what percent of all samples are less. Let me rephrase that. Let's say have a mean less than 70. What percent of all samples have a mean less than 70? Draw the curve. Not a great curve here, but 0. I'm at 1.67. Actually, this is negative. Sorry about that. It's a negative 1.67 because it's a negative 5 on top. So I want negative 1.67. So I want this tail. So we're going to look this up in the table again. We're going to look up positive 1.67, and we're going to look at column C to find the amount that are less. And we look up 1.67, we look up column C, we get 0.0475. 0.0475 in here. As a percentage, move the decimal 2 places to the right. This should be 4.75%. Of all sample means from this population that has a mean of 75 and a standard deviation of 15, 4.75% of all sample means would be less than this, less than a mean of 70. So not much, right? So then that also is the question, like, does this sample belong to this population if there's only less than 5% of samples that would be less than it? And most of the time we would say no, it belongs to some population with a smaller mean than 75, right? If I want to ask what percentage of scores are greater than this, I would just do 100 minus 4.75. And you do this the same way you did the one sample test, same table. Now, when we get to hypothesis testing in a little more depth, we're going to be talking about rejecting the null hypothesis, right? So eventually we're going to have like cutoffs. We're going to have cutoff z-scores. And if your z-score is greater than or less than the negative version, right, of the cutoff z-score, you're going to reject. And if it's not less than, you're going to fail to reject. But what we're doing right here is we're establishing the sampling distribution of the mean. That's the important part here. And we're sort of getting a framework that we're going to compare our sample. So this is our sample, which hopefully has an effective treatment, right? So our sample that we did something to, some kind of intervention, right? We're comparing it to the population that represents the null hypothesis when the null is true. The null hypothesis basically means no effect. So we're saying, let me write that a little better. So my L became a T. We're saying, is our sample consistent or typical of a sample from a population where the null is true? So is our sample that undergoes a treatment typical of a sample drawn from a population where the null hypothesis is true, where there's no effect? And if the answer is yes, yes, it is common to the population. If that's the case, we're going to fail to reject the null hypothesis. If, however, our sample, which is our treated sample, or intervention, whatever it is, whatever we're doing, is different, is unlikely to be drawn from this population. Unlikely. We can say that, less than 5%, right? Because that's the criterion we use a lot. If it's unlikely to be drawn from this population where the null is true, then we're going to reject the null. So it's always comparing our sample, which represents the treatment, right, or the intervention, because that's what we're doing our intervention on. We're doing the intervention on the sample. We're not doing it on the population. Population is too big. We do our treatment or intervention on the sample, and then we compare that sample to the population where the null is true, the population where there's no effect. There's no the intervention doesn't work. What would we expect if there was no difference with the intervention or the treatment? And then we say, is it likely to come from that population where basically the treatment doesn't work? Or is it unlikely? If it's common, fail to reject the null. If it's uncommon, reject the null. And that's the basis of all hypothesis testing with samples, which is pretty much everything. Now, we're using Z when the sample size is greater or equal to 30, right? And we know sigma. And this is the important part. We know sigma. So we have to know the population standard deviation to use Z. Most of the time we don't know the population standard deviation. If we do not know sigma, we cannot use Z. We have to use an alternative. And that alternative is going to be known as T. And that's going to be the next hypothesis test that we cover. But we cannot use Z unless we know sigma and we have a big sample, or we know the population is normally distributed, right? If we don't have any of that stuff, we don't know sigma especially, that we cannot use Z. And we're going to get to that in the future, but it's good to know that Z it's useful when we know sigma. Most of the time, we don't know. And that's pretty much it. So hopefully that helps you understand the idea of sampling distribution of the mean and why it's so important and why it represents the null hypothesis and how we're going to be comparing all of our samples to the sampling distribution of the mean and then deciding to either reject or fail to reject. And it's a complicated topic, but try to soak in as much as you can. You're not going to get everything the first go around, but ask questions. You can always ask me questions in class, send me emails, etc. I will try to explain it the best way I can, which is what I'm doing here. And hopefully some of that sinks in and you understand the one sample Z-test that we're going to be conducting in the future. So hopefully that helps. Let me know if there's any questions, and I'll see you online next time.